That's weird. The message on my Mac when I start recording says this meeting is being recorded, but when I use the PC, which is what I'm using, it says recording in progress. Weird. I hope we're getting it. Anyway, all new and wonderful. Binary numbers. So the first thing to remember is that in the world that we're living in, right, time is a continuous phenomena. It's important because digital is not. And as a result of digital not being continuous, that in order to do anything digital, we have to stop and measure. So, automatically with digital, you're going to lose information, right? So the world that we live in is continuous. There's no breaks. There's no such thing as sampling. Someone once said the arrow of time carries on going forward no matter what. And the other thing is we experience the entirety of our existence all at once, right? So, whereas in a digital world, time is sampled. We take the world apart into pieces and examine and measure it. So analog is defined as something that is similar or comparable to something else in either general or in specific detail, right? So analog isn't necessarily the opposite of digital, although we've come to use it that way. What analog means is that we're making a copy of reality in a medium that allows it to be copied in its entirety. So for example, recording an analog audio signal, you get an electrical signal that moves exactly instant for instant, moment for moment, in the same speed, time, and magnitude, and frequency and wavelength as the original signal does, right? And that's how it's different than digital. Digital does not do that. So an analog clock moves continuously like time does. So again, the key thing to remember with analog technology is continuously variable. Okay, so it's a copy like the photocopy would be analog, although today that's actually not true anymore because photocopies are digitized and then reproduced as with analog. But nonetheless, analog is a copy of the event. Digital is not a copy of the event. So digital is using the numbers. And what we do with digital is we take reality and we break it into chunks and we assign values to it. So the case of the clock metaphor, where an analog clock, we'll go back to the clock for a second. The analog clock will move continuously, although some clocks have second hands that tick. A lot of them will have a second hand that sweeps along. And in any case, the mechanism inside the clock is moving all the time. In a digital clock, it isn't. Digital clock will show you a number for a moment, and then when that value changes, when we have enough time go by, for example, to move to the next second, then the second value will change up one more digit, right? So we're really just getting a sample. And so what you can understand right away, for example, with a clock, you can watch a clock change from 1 second to the next. So what that means is that there's events occurring between those two instances. So in this clock here, we're seeing 05:52:03. The next instant will be 05:52:04. However, a human being can watch it change from 03 to 04, which means you're aware of the fact that between the 3 and 4, something's occurred, right? Whereas in digital, it isn't. Digital is saying we're at this instant and then we're at that instant, right? We jump to the next second. So digital will use numbers to describe phenomena, right? That's the whole point there. And it sounds obvious, but I just want to make sure that you're clear about that, because when we start talking about digital, one of the big issues with digital, unlike analog, is that everything has to be mathematically processed because we've turned it into numbers. Analog isn't mathematically processed. There's no CPUs required to record and play back an analog signal, right? They're optional, but they're certainly not required. Whereas in digital, you have to have mathematics happening all the time. So basic digital devices are examining and measuring continuous phenomena. So what's the difference? Oh, hang on a second, I'll pause. It's got a couple of people there. All right, so what's the difference? The difference is that analog is continuous. It's a copy. It's a copy that loses detail each time, because there's no way to copy the original event in any way. Like we can't, if we shoot with analog film, for example, we're not capturing an instant of reality. We're just capturing on film a chemical reaction that simulates the retinal reaction of our eye. It's not perfect because it's not our eye. So every copy that you make in analog is going to lose a bit of detail due to the medium that you're copying with, right? So that is one of the downsides of analog. It's in real time. So the analog recording can continue as long as you have recording material, and there'll be no missed data anywhere in that process. In the sense of a time, in sense of time, you won't miss any data because of the time. You'll miss data because the copy detail won't be the same. In digital, it's momentary. So we stop and freeze and measure. We stop and freeze and measure, right? Something called sample and hold. So you sample, you hold a signal. It's actually called hold and sample, but we call it for some reason sample and hold. You grab a piece of information, you hold it for an instant, you measure it, and then you go on to the next one, right? The advantage to digital with the giant asterisk is each copy of the copy is the same because it's all numbers. So as long as you copy the numbers faithfully, and that's what the asterisk is all about, it's the same. There's an illusion, or I shouldn't say an illusion, a misapprehension that digital copies are all identical, and they're not. And we'll talk about that later when we talk about being a DIT on set, a digital intermediate technician, because one of their jobs is to copy the files from the camera to a hard drive. And simply copying it the way you would copy any file on your computer is not good enough, because those copies you'd go from computer to computer aren't necessarily faithful. They are. So when you copy files from one to another, a lot of shortcuts are made to make it convenient for you. And one of those shortcuts is that as long as the file is close enough to the original, then that nobody notices it and it doesn't corrupt the file, then that's good enough. In the film business, in the movie business, and television business, when you copy a file, it has to be exactly the same. And so we apply extra steps to make sure those digital copies are identical, right? Because and otherwise you end up with corruption. The data gets corrupted, especially if you compress anything. If you zip something or compress it, that data will change. Anyway, we'll talk about that a little more later. It's not real time, the final step about digital. It's not real time because in order for you to hold it and measure it, you've got to stop recording, right? We haven't got a digital technology yet that allows us to continuously record every instant of every event. Now, when I say, I'm being very dogmatic here, apparently it's fast enough that we don't notice we're not recording everything. And that's the key takeaway, right? The difference is that we aren't recording everything because we have to stop. So your sampling rate is how often you stop, or conversely, how often you capture. And every capture is a momentary hesitation while you stop recording, measure the data, and then record the next sample. Okay, so that's the one I'd say not real time. But it's done fast enough, and again, it wouldn't be practical if it wasn't fast enough that we don't notice that we've stopped. So binary numbers, how do they work? Well, let's talk a little bit about that. So for those that don't know, and this might, for some of you, this might be very, very basic, but I want to make sure that we're all at the same level when we carry forward. We're going to talk about that and say that binary means 2, right? So 2 digits, 1 and 0. And the big question with binary, of course, is how do you show big amounts with only 2 digits? We talk about how we count. So let's have a quick kindergarten lesson for everybody. You want to sit down, pull up your little rug, and I'm going to have a little sip of my tea. And we're going to talk about how we count. Okay, so an example of a counting system, remembering that back far enough in human history, we didn't have numbers. So what people used to do is things like tally sticks. There's all kinds of methods we had for counting. And one way would be, for example, if you want to have 24 eggs for sale, you might write down that I have and then make 24 dots, eggs for sale, and then leave that to the other person to count the number of dots and go, oh, okay, 24, perfect. Romans would write down, they had a code. So they didn't use the dots anymore. They had a code, and they would have XXI eggs for sale. And that's not 24, is it? Yeah, they wouldn't write XXI eggs for sale, but they would write, Roman numerals. Oh, it is 21. Wait a minute, I said 24, didn't I? Yes. Okay, never mind. Somewhere I switched from 24 to 21. So let's say the Romans decided they took away 3 eggs for tax to pay the emperor. And all you had left was 21 eggs. And so anyway, where was I? I'm pleased with my own joke. So the Romans would write down XXI for eggs, saying that they had 21 eggs, 2 X's, 1 would be required, for 10 and 10 each, and then I for 1. And of course, they weren't called X and I in Latin. I'm not exactly sure how they were pronounced, but that's just the letters we use today. This is called, and the reason I say that, this is called sign value notation. And so once you get past tallying and simply putting a mark for each item, you get into something called sign value notation. And what that means is there's a different symbol for different values. All right. So in the case of the Roman numera bet, whatever you want to call it, numbers, X was 10, I was 1, V was 5, right? They had a whole bunch of values. It's possible with this system to write out a large number with only a few symbols, right? But the problem is you have to remember what all the symbols mean. Okay, which means you have to have a dictionary somewhere in your head, and we all learn this. Like all of us have learned some sort of counting system, whether it's the Roman numerals that we use today, or the Arabic numerals we use today. Whatever numbering system you've learned is in your head. You had to memorize, right? And where that becomes obvious when you go like that's easy. Well, think about putting it into words. So it's one thing to see the symbols, but of course every language has a different word for that same symbol, right? So you have to have this in your head, this sort of code book. So in our system, we use what's called Arabic numbers, and that's in quotes because there is some contention about who, and I'll be honest, there's, especially in the last 50 years, there's a real loadedness to the word Arabic, and some people I think might resent that word, and I think that's unfortunate because it does appear that at least the number 0 came from the Middle East and Muslim Islamic mathematicians. But anyway, moving on. That's why it's in quotes, in case you're wondering. There is some contention about it. It's become a little politicized, of course, as everything seems to nowadays. So, there's an internet adage nowadays, by the way, as a sidebar. If you ever want to have a disagreement, just state a fact, and you'll find someone who disagrees with that fact. So we use a decimal system, right? And decimal meaning a system of 10 digits, 10 symbols, and they go from 0 for nothing to 9. So when you think about it, we have no symbol for 10, right? And that's important to remember when we start talking about binary. There's only a symbol. The highest value we have is 9, but there's 10 symbols, decimal numbers, because 0 is a value, right? That's called sign value notation. How do we count higher than 9 if we don't have a symbol for 10? We reuse the symbols. So we do a hybrid. So we don't have, like some systems would have increasing digits. For example, hexadecimal computer code would have 6 extra digits to get you up to 16, right? Extra symbols, and they use combinations of letters and numbers for that. But we instead do a hybrid now. We do something called positional notation. So we take the symbols and we change their position, right? And again, you all know this stuff. It's really fundamental, but it's important because binary uses a similar kind of process. We take the tally. We start on the left with the tally system, which is just 1 dot for everything. We then have words in the center, and those words are changed in every language. But on the far right, we have the positions. So the 1 becomes a 10 when you move the 1 to the left and put a 0 beside it, right? And again, we know this from learning that now what we're saying is we have 1 10 and no 1s, right? And 2 1s and 1 10 is 12, and 2 10s is 20. Okay. And again, in some languages, French is one example. You will just simply start stating that 20 number, and we do it a little bit, but we say 25, 26, 27. So English is even doing the same thing, right? Where we're using the 20 over and over again in that series of numbers. We don't have a unique name for each number above 20. We do, but it's a combination of other names. We don't have a different word like, Fnargle for 21, right? And then 100, of course, is the third column, okay? So each position in decimal positional notation, each position, when I say position, I mean column, position to the left of the base digit, is 10 times greater than the one to the right, okay? So in the case of 100, you move 3 columns over, it's 10 times 10, right? One more position over, and I don't show it, although I have it written down here. If you move that 1 over 1 more position, you'd have 1,000, because it would now be 10 times 100. Right? So it's just 10 times 10 times 10 times 10. And again, we know all this instinctively because that's our base counting system. And as I said before, if we use like a hexadecimal system with 16 symbols, the position to the left would be 16 times greater, all right? So the problem is for a computer, and we go back to digital now, why do we have just 2 digits? Because all those symbols add complexity, right? Computing needed, especially when we talk about the early days of computing, when memory and programming and software was super valuable space. So they had to come up with a way to count numbers using the least amount of software and programming possible, and hardware for that matter. And so they decided, for a number of reasons, that they had to only have to have two symbols. And one symbol would indicate that there was an item, and one would indicate that there was no item. And then using that, they would build a whole code out of it, right? So with two symbols, you need more columns, but you don't need more digits. So the thing about that is your dictionary in your head to translate the digits is really only two things. There's either something there or nothing there. There's not 9 somethings there, or remembering that this is 9 or that is 8 or this is 7. There's no uniqueness other than there's something there or nothing there. Now they could have used anything else, but part of the reason they used numbers when they started out with digital is people have to read this. And so they needed to have something that humans could also look at. Because original binary code was manually created with human beings, right? And it was simpler just to use existing symbols like 0 and 1. So in binary, the way we count, we just simply add columns. And because in the decimal system, the column to the left is 10 times, because there's 10 base digits, in binary, there's only 2 base digits. So the column to the left is only 2 times higher, right? So the first column is 0 and then 1, and then you're out of digits. So then you say, now we have no more 1s, which is the third one down, but we have 1 in the 2's column, because it's 1 column to the left is now twice as much as everything in the first column. So we have 1 in the 2's column, that's 2. So 2 in binary is 1, 0. Right? And then 3 is 2 plus 1, which shows as 11. We would use the word 11, but it's actually 3. And then 4, you add another column. It's now 2 times 2, because the first column is the base column, the second column is 2, the third column is 4. 2, 4, 8, 16, and on, right? And if we go down to the bottom and see 8, it looks like 1,000 because there's nothing in the 1s, there's nothing in the 2s, there's nothing in the 4s, there's one thing in the 8s. And 9 would be 8 plus 1. So that's the binary system kind of in a nutshell, using these positions. All right. Questions? Everyone's kind of cool with this? I hope so. By the way, just so you know, you're doing better than most classes, just judging from your reaction, because in past years, especially when I started doing this binary lecture about 5 or 6 years ago, I just got these blank looks like, what is going on? So I'm glad you're getting it. So why do we choose binary? What was the whole point of binary? It's because we used electricity. Early analog computers, when I say analog, computers without solid state circuitry that used tubes and light bulbs and all kinds of other fancy mechanical stuff. Google it if you don't believe me. Computers were huge and had tons of hardware. But anyway, the only thing that was reliable was electricity as a way. I mean, people tried to design computers with water. You know, Babbage, if you go back far enough, Babbage designed a loom system for fabrics, and you probably heard about Babbage. And Ada Lovelace, who helped him, and some would argue, did all the software, if you want, for looms. And Babbage used a punch card, and his system used holes. There was a hole, you did something, there was no hole in the card, you did nothing, right? And that carried forward right up until the 1980s, when we kept using paper punch cards. But nonetheless, we used electricity because it was reliable, we could make it, we could measure it. And the only reliable state of electricity is on and off. Otherwise, you end up with having to measure voltage, current, right? As we know, electricity has a whole bunch of properties. But the one thing you can say about electricity, it's either there or it isn't there. And that's definitive. There's no need to measure it other than witness it. So they figured, okay, we'll just say that. We'll use an open switch. If the circuit's active, in a closed circuit, we have a 1. If the circuit's open, we have nothing. We have no electricity. So 2 states, and it's dead simple, right? And that's, to this moment in time, that's how all computers are operating even now. They're basically manipulating these 2 states of electricity for us to have the internet, to do Zoom, to have video, to have cameras. All that stuff is still underpinning everything, and probably will. When people talk about things like quantum computing, all they do is they transfer or exchange the electrons for photons. The actions are still the same. Okay. So 2 states, 2 digits, I kind of said that. On is 1, off is 0. And again, the shorthand, we've gotten so used to that now. Our parents and grandparents might look at a device that has a button, a switch on it with a 0 and a 1, and not know what it means. Well, we're so conditioned now to that binary idea. When you see a switch that has 0 and 1, you think, oh, that's the power switch. 1 is on, 0 is off, right? So we're conditioning ourselves now to look at binary. And in fact, Apple's symbol, I think Apple's symbol for the power switch is kind of a stylized circle with a line kind of in it, kind of indicating both the 0 and the 1. So, you know, everyone's going for it. Anyway, one binary digit is a bit, right? So one of these numbers here, like this 0, that's 1 bit, 2 bits, 3 bits, 4 bits, 5 bits, 6, 7. 8 binary data bits are a byte. This is also important because when we talk about data streaming, we always, and this is probably historical, but we measure in bits, gigabits per time frame, megabits per time frame. So megabits per second, gigabits per second. That is how you measure bandwidth, right? But memory is always measured in bytes. And that's probably because memory is static. You know, digital memory isn't moving, and therefore we don't really care about how quickly it's appearing. We care about how much of it there is. It's a lot more difficult to calculate how much data there is in a digital bit stream. You have to do a bit of math, right? But it's easy to figure out how much data there is in a byte because it's 8 bits to a byte and it's not moving. So storage is always storage is always megabytes, gigabytes, terabytes, petabytes, and data streaming is always gigabits, megabits, petabits per second, right? Streaming is always in a time frame. So the thing with a bit is there's no such thing as an empty bit. It's always got to be 0 or 1, okay? Now, there could be empty bits in the sense that it's unused, and one of the things, depending on your computer, you know, your mileage may vary, blah, 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 is that you might end up with a computer that doesn't recognize a piece of memory as active because there's nothing in it at all, right? But that's not usable information. There's no data there. The computer's going to say that bit has no 1 or 0 in it, therefore it's invalid. So typically, when we erase a hard drive, for example, we fill all the bits up with zeros, right? We turn them all basically off, or we tell the computer that they're off. They're not off. There's a 0 in them. There's something there, but there's always either a 0 or a 1 when we talk about binary. There's never a blank state, a null state. So zeros and ones are great. Those are bits. We need groups of bits to go and count higher, so we have bytes, right? And these are the 8 spots. Here's a byte, 8 values of 1, right? 8 bits is a byte. I'm going to keep repeating that because when we talk about some of the math you're going to have to do, for example, we'll do it later today, we're going to convert data rate into storage rate. So in other words, if your camera will produce, you know, 1 gigabit per second, how much RAM, how much storage do you need? Well, you can figure that out, right? You take that gigabit per second and you divide it by 8, which I can't do in my head off the top of my head, but you divide it by 8, and now you know how many megabits per second. So I bet, yeah, it'll be at least megabits per second. Or sorry, let's try that again. You take a gigabit per second divided by 8, you know how many megabytes per second that hard drive is going to fill up with, right? So you can get a rough idea of your kind of storage if you know the data rate of your device. And again, that becomes important when we'll talk a little later on this term about compression and what decisions to make regarding what to compress, how much compression to use. Okay, so bit versus byte. As I said, a bit is 1 value, so a byte has 8 bits in it. A bit has no bytes in it. Sometimes a bit or a byte, pardon me, sometimes it's called a word. And keeping, again, just to remind the positional notation that every bit to the left, so if we go back to this illustration of the byte, you know, every one of these is 2 times more than the one before. So these are all full, right? So it's basically 2 times 2 times 2 times 2 times 2 times 2 times 2, and you're going to end up with a +1. So remember, this is the base column. So then it's 2 times 2 times 2 times 2 times 2. It's 255 when you get to here, and then you add the 1 for 256, right? So 8 bits will give you a maximum value of 256. No, I'm sorry. I just misled you. Let me start that again. If you take all these together, you get 255. If you add that, 254 plus 1 is 255, but you get 256 values when you take all these columns and make them 0. Because that's one more value we didn't include here, which is all these being 0. So it's 255 if you add all these numbers together. And then take this byte, empty them all to zeros, that's 256. So 8 bits, 1 byte will give you a maximum value of 256. Well, I'll go over that again, by the way, just so we're not too unclear about it. All right. So here we go. Here's it showing. And each value doubles as you go, right? 1, 2, 8, 4, 8, 16, 32, 64, 128, etc. So to figure the decimal value out, just simply take the 2 columns and add the values. So for those that are confused about this, and you see 128 out here, right? And you're thinking, you just told me 256, Mike. Why is it now 128? Because remember, to get 256, you have to fill up all these boxes. Well, then to follow this math, you have to add them all up. So you add the 128 to the 64 to the 32, right? To the 16 to the 8 to the 4 to the 2. Okay, but when you add the values across, just take any boxes that have ones in them, and remember that it's 2, 4, 8, 16, 32, 64, 128, right? And add 32 and 8, you get 40. So this is 40. We typically trim these leading numbers off. I say that because if you give me an answer in a quiz with the leading numbers on or off, it doesn't change the value of the number. The leading numbers on the left are 0, right? So that doesn't add to anything. So never trim off anything up that's a 1, but always, if there's zeros to the left, you can trim them off. The only time you would never trim it off is if the answer requires you to show it in a byte, all 8 digits, right? And sometimes that's the case. Like a computer would always want all the digits full. So a computer would show 00100, or sorry, 00101, because the computer needs to see everything. Humans can assume that these 2 are empty and we can just trim them off. And that's binary numbers. But wait, I know. This works better live, but what the heck. I just want to go over that again, right? Because those of you that are confused, you're seeing 128. And I say that because some people are very concrete thinkers, and that's a great thing. But you see that 128 and you can't get into your head, why is it not 255, 256? So here it is, explained. So the 128 plus 64 plus 32 plus 16 plus 8, 4, 2, and 1 equals 255. And where is 256? It's this. Because when you start with this, you start with them all blank. And 0 is a value, all right? So in the case of color, I'll jump a bit to the color. So Photoshop 8-bit color, the maximum value is 255. Why is that? Because 255 is the biggest decimal number you can make. So this is where I need you to think clearly here. Decimal number isn't value, right? It's a value, but the value could be any assigned number. Decimal number means specifically when you do the math and convert this binary number into a decimal number, the highest decimal value is 255. That's correct. But the total value of digits, there's an extra digit hiding here, and that is when they're all blank. So that is considered a value. Again, to a computer, this is important information, that there's nothing. To us, it's important information because if this were, for example, the color red in Photoshop right now, and we had green and blue full up at 255, there'd be no red. If all 3 colors were 0, there'd be black. So that is in fact a color, it's a value, right? But it's not, we often don't consider 0 to be a number. And we confuse the decimal number with its value. All right. And just for those that aren't quite getting it, here's a binary number joke. Getting it? Yes, no? Yeah. How many people are reading it as there are 10 kinds of people in this world? Nobody? Because if you are, you don't get it. Because there aren't 10 kinds of people in this world, there are 2 kinds of people in it. This is the number 2 in binary. Right? There are 2 kinds of people in this world, those who understand binary and those who don't. All right, that's it. Stop share. Pause recording. Actually, stop recording.